And we are going to have the first lecture of another series of lectures, which is about string compactifications, geometry, and effective field theories by Lara Anderson from Virginia Tech.
Thank you very much. Could everybody hear me all right? Yeah? So just to begin, I would like to share that when I was a PhD student, I was studying in Oxford, and this was the very first, graduate program summer school that I ever went to as a student, the ICTP Spring School. And it was an overwhelming and also very exciting experience for me. I made lots of friends as fellow students who were people that I, later collaborated with and have been good friends for many years. And also, I realized recently that several of the people that lectured at the school when I was there, I have now collaborated with and applied for funding with. So just to say that I think this is a wonderful opportunity to bring people together, and you never know who amongst the people that you're talking to you're going to work with in the future. So I hope you can foster all those conversations. So to begin, I'm going to be talking about string compactifications. This is an extremely broad and very old subject. This dates back approximately the full 40 years that Bobby alluded to at the beginning. And there's a lot of things that one could say. My goal is not to review every possible aspect of string compactifications, because that's impossible in a few lectures, but to give you a flavor both of the sort of central questions that arise in this subject, and then I'll allude to some of the newer results and areas of interest that are currently being studied. So here's a very broad question. We want to ask, what EFTs can arise from string theory? This is, of course, huge, and we don't even need to be in the subject of string geometry or compactification to ask it. But even if we begin with the standard set of beginning in, say, 10, 11, maybe 12 dimensions, and then reducing a theory down to lower dimensions, for example, 40, this question is a very difficult one to answer. Okay, so even in the class of geometric compactifications, what we want to understand is something like the following diagram. We want to ask if this is all QFTs possibly coupled to gravity in any number of dimensions. You could ask which ones arise from string theory. And then I'm going to have as a subset of that whatever you care about. Now, what do we care about? We'll call it pheno. Maybe it's not pheno, maybe it's some other feature of effective field theory, but whether we care about particle physics, cosmology, finding a solution of string theory that looks like our universe, right? We would like to understand roughly how the structure of this Venn diagram works. One thing that has been studied very extensively over the last 40 years is that in high numbers of dimensions, so reductions of, say, 10-dimensional string theories down to 8 or 6 dimensions, at least at the level of quantum field theories coupled to gravity supersymmetrically, this diagram is essentially complete in that almost every consistent, supersymmetric gauge theory coupled to gravity that you can write down in 8 or 6 dimensions can arise from string theory. Of course, the pheno part is kind of absent in 8 or 6 dimensions, but we understand that string theory can sweep out a huge array of the possible consistent and completable quantum field theories in that sense. But in lower numbers of dimensions, 40, we have no idea. Right? So it could be that this, the central box, depending on the question of interest, whether this is de Sitter vacua in string theory or finding a solution of string theory that looks like the standard model of particle physics, this could be empty, right? There could be no solutions of string theory that do that. So in the context of beginning with higher dimensional theories and compactifying to reduce 40, here we're considering solutions of, say, some 10-dimensional space as, for example, Minkowski space across some compact 6-dimensional space. We'll get more into this in a minute, but this is what I have in mind for geometry, some internal directions of string theory. We replace the question at hand with what QFT now gets replaced with what geometry. Okay. So what geometries are available as backgrounds that can produce quantum field theories of interest? One thing that has also emerged over the last 40 years is that there is a huge multiplicity of such solutions. So you may have heard of the so-called string landscape, 10 to the 500, question mark. Many, many, many string vacua are possible. So there might be a tendency, perhaps in the field, perhaps for individuals, to say, in so many possible solutions, what's the point of asking the question that I just did, right? Like, surely in this great multiplicity of solutions, there's some solution that looks like whatever you want. I personally think this is a very misleading way to think about it. So for example, in the oft-quoted 10 to the 500, flux vacua of string theory, none of these solutions have an electron in that background. So if you are interested in structure, can you have de Sitter vacua? Can you have particle spectra like we see? It is not the case that anything goes. On the contrary, it could very well be the case that nothing goes, right? That we could just rule out whole arenas of string theory. So I want to make the argument that this is not a vacuous question. So not anything is possible. So instead, we want to understand what constraints arise. And in particular, these lectures, I'm going to try and ask or illustrate the geometry and effective theory interplay. So if you choose a geometry, what does that tell you about the effective theory? Centrally, as I mentioned, constraints. So can we understand which classes of effective theories are viable? And then here's a big one. We want to understand how many. So are these bounded? Are these finite? Can we classify their general properties? And there is multiplicity in the space of solutions to string theory in the sense that more than one geometry can lead to the same effective physics in a string dimensional reduction. And so this, of course, is the subject of string dualities, but as it applies here to string compactifications. So we want to understand, again, if there's 10 to the large number of ways of all producing the same effective field theory, you want to understand that in terms of classifying what can arise. Okay, so these are broad questions that I want to illustrate. Just to comment on, my own personal research and what are my motivations, I am very interested in the question of whether there can be solutions of string theory that do resemble our world, right? There are lots of very good reasons to study string theory, even if no solutions of string theory look like our universe. For example, understanding the structure of quantum gravity at a deeper level, it's a perfectly good reason to study string theory. But for me personally, I'm very interested in, can string theory do this? And if it can't, can we understand the consequences of that for the right theory of quantum gravity for our universe? So my personal motivations are trying to understand in this pheno box here things like particle physics and cosmology in the string context. And we need to pick some arenas to illustrate this. Just in very broad brushstrokes, so arenas that you might consider in order to produce some solutions of string theory that look at least a little bit like our world. This includes compactifications of heterotic string theory, M theory, F theory, and things like 2B orientafolds. I will touch on a number of these over the course of the lectures in the next few days, not in any depth, but just to illustrate some of the things that can arise. Good. Just as a context here, in order to ask these questions, we're going to start, because this is really about how geometry could affect or bound our quantum field theories. Obviously, we have to set up the basics and the constraints of the geometry. So this is a lot of math. This is just a preview to say that I'm going to be dumping a lot of math on you to begin with, and then as the lectures go on, we'll try and see what the consequences of some of that math are. So hang in there, and hopefully it'll be worth the trip. All right. So to begin, let's just pick one arena to look at this. So as illustration of a string compactification, let's consider the heterotic string in 10 dimensions.
Can I?
Sorry, was there a question?
Yeah, can I ask about the
Sure.
motivation question? So there are also QFTs or models where you can get some quantum field theory living on top of brains, or some brain constructions, which you can then couple to gravity through, if they don't necessarily decouple.
Sure.
Gravity
So you're
in the higher
saying,
dimensions.
domain walls, brain worlds, yeah, et cetera.
Is this a subset of the types of theories that you're studying here, or are these constraints completely? Is it completely
I would
different?
say it's not absolutely a subset, but in many cases closely related. So certainly, to give an example, heterotic M theory, where you're compactifying M3 on an S1 mod Z2 orbifold, this is very much one of those brain world scenarios. that again, falls in the context of string compactifications. You can ask Brain World or, other pictures without this technology, but there's a substantial overlap in cases. I should make the caveat as well that I'm very much interested in coupling in the closed string sector and the gravitational physics in this question. So if you're just asking about QFTs in assorted dimensions, if we don't demand UV completion, there's of course many things that can't arise in string theory. Good question. Other ones? Okay. So we're going to do heterotic string theory. To start with, this would be the E8 cross E8 heterotic string in 10 dimensions. Why this one? Just because it has a lot of the knobs that I want to illustrate that you can turn, but much of what I'm going to say is going to be more general than this, and I will illustrate where that comes in. Okay, so how does this kind of string dimensional reduction go? As you've probably seen at some point before, you begin in various 10D actions, things that look roughly like this. I should say, by the way, as a quick caveat, I am not going to basically give any references on the board, but I will try and post my lecture notes that have lots of reading and references as people go through. So I apologize in advance for the lack of references. So here is a 10D Lagrangian. And this comes, in the case of the heterotic string, with a Bianchi identity. That looks something like this. And in terms of the field content and multiplets, we have a Yang-Mills multiplet, which involves a gauge field in 10 dimensions and a gaugino. We have Sugra multiplets, which includes a Vielbein, a NS2 form, B field, the dilaton, a gravitino, and a dilatino. And here, in terms, as we'll see in a moment, this 2 form, D of this, is related to the 3 form, H, which appears in this Bianchi identity. Okay. So beginning with one of these 10D supersymmetric theories, we have SUSY transformations. That must be satisfied. So if we consider spinor variations, these take the following form. Where here I'm being fairly schematic. Here H with 1 index, so no indices, are various contractions of the 3 form with gamma matrices. Etc. Okay, so here I am parameterizing the supersymmetry variation in terms of this guy epsilon. This is a 16 component 10D Mordell-Weil spinor. And the question is, can I find, for this 10-dimensional theory, solutions of the theory that are going to compactify some number of those 10 dimensions, reduce down to a lower set of dimensions, I'm going to consider 4 to begin with, that will preserve some aspect of this supersymmetry. A fair question might be, why do we want to preserve supersymmetry? Because we don't see it in nature. And the main answer is twofold. The supersymmetry at the level of a compactification scale so the size of these compact extra dimensions, has uses in terms of, for example, protecting the Higgs mass. And also, perhaps the most important one, is that we maintain computational control of the theory with a large degree of supersymmetry, or even any supersymmetry. We have computational control of the theory in order to write down the 4D effective theory. That isn't to say that we aren't going to break supersymmetry later. Of course, we need to in order to find realistic vacua, but we want to separate the scales so that we can use supersymmetry to some extent and then remove it later on. So to begin, in summary, we'll consider solutions in 4D with n equals 1 SUSY. Might say why n equals 1 and not n equals 2. The primary reason for that is that this will allow chiral fermions. Unlike in n equals 2 theories, in n equals 1 theories, we can at least have families and no anti-families like you see in the standard model. And another reason might be, for example, to protect Higgs mass. Good. So if you want to begin with n equals 1 solutions, let's look for solutions of the theory that are of the form, as we mentioned, let's more generally say M4 cross M6, where the game is going to be to make this a compact set of extra dimensions whose distance scale is small enough to be consistent with observation. We're going to make an ansatz for the SUSY parameter, which is that this epsilon should be a product of spinors in my assorted dimensions here. So this will be the 4D guy, and this one, say, a 6D part. And in particular, at the level of the SO19 symmetry of the 10-dimensional space, I'm looking for solutions that go as SO13 cross SO6. And in terms of the spinor representations, this means the 16 spinor has to include a 2-4 and a 2' 4 bar. Okay, so we're choosing to preserve 1/4 of the 10D supersymmetry. Where did I put? So choice to preserve 1/4 of 10D SUSY. And so of the possible 4 etas that we might consider here, we're going to choose just one. So of 4 etas, choose one, and we'll call it eta naught. That is our preferred one. And now, in order to preserve that symmetry in 4 dimensions, we have to go back to our SUSY variations and demand that they vanish at least for that one direction. So in particular, we're going to demand that 0 is equal to delta eta naught psi m, which is going to be beta cross eta naught h m beta cross eta naught, and so on. Delta lambda will be d bar phi theta cross eta naught plus, and is this too low, by the way? Can people see this down here? Kind of okay? Tell me if I'm too low. Okay. Which will be gamma fa eta naught, and so on. Okay. So far, nothing too complicated has arisen. Let's explore what can happen. So as I mentioned, we're interested in solutions of the form M4 cross M6. Let's consider M4, so I'll write this again, M4 cross M6. We want this space to be maximally symmetric. And as we said previously, this one is compact. Various examples we will consider of this. This implies that for the 3 form, if you have mixed index structure on this 3 form, and for the dilaton that these equal 0, where here mu nu will be 40 indices, so running 0, 1, 2, 3, and ij 60. So basically, if you have mixed index structure across the 3 form, if you had something like this, your space would not be maximally symmetric if this were non-zero in vacuum. So you want to demand that that's 0, and that your dilaton is not varying in the spacetime. Okay, so this leads to, if I consider these equations, actually, let me write it this way. So things that this constraint leads to, let me write these spinor variations again slightly more explicitly. In the compact directions over the internal space, are 60 M6, I'm calling it here. We have conditions that look like this. This guy must be 0. I'm calling this equation 1. And 2, delta psi mu is this one. An integrability condition follows from that. Which is this guy. And this implies that R40 is 0, i.e. that M4 is Minkowski space. So if we look at 1 in this context, this tells us that delta lambda is a constraint like this. Acting on eta naught is 0. And let me write it here as well. Psi A is gamma ij fa ij eta naught is 0. Where F here is the field strength of the associated 10D gauge fields. All right, now that we have all these supersymmetry variations on the board, we can start to actually ask about general properties of the solution. So from the equation that I've labeled 1 here, we see that this operator, nabla I over the compact internal space plus an eighth h, this is effectively a derivative operator that acts on eta naught. Okay. If there was no h term in background, then this would just be the statement that eta is a covariantly constant spinor. We'll come to that special case in a moment, but for right now, let's remain general. So in order for this to parameterize the supersymmetry that I am interested in, I need that eta naught is nowhere vanishing, but not quite covariantly constant. There is a name for such a space. So let's say it, eta naught, nowhere vanishing, and not covariantly constant, but satisfying this derivative operator is 0 on eta naught is 0. A space that does this is referred to as an SU3 structure space. We'll talk about the special case in just a moment where that SU3 structure gets upgraded to SU3 holonomy. That's in the case of no flux. So if it's just a covariantly constant spinor, this will be about the holonomy group of the underlying manifold. This is SU3 structure. So rough idea, what does it mean to be SU3 structure? What is this talking about? Here we have, of course, a spinor of SO6. That was part of our decomposition from 10D. And this is the fundamental of SU4. So we can choose, locally at least, local transformation to put this in the form for some patch as a bunch of zeros and something. Okay? Now, if I consider the transition functions on my manifold, so we'll consider patches ui, uj, and we have a tij transition functions that moves us between such patches. Then these must have the following property with regard to our spinner. If we want this to remain the one component spinner in SU4 that we're interested in, then we need this to be preserved. So generally, of course, T would be a full element of SU4, but here, T has to break down if we want this form. So if we're going to demand that this is true, in order to keep our one supersymmetry, this must have the following form. So here's the origin of the name SU3. This is SU3 because the transition functions on the manifold can't be generic elements of SU4. They have to reduce to an SU3 component, or SU3 block. More formally, you can say that the structure group of the frame bundle is reduced. So also, structure group of frame bundle is reduced from SO6 to SU3 in the presence of demanding this nowhere vanishing spinner. Okay, so far so good. What do we want to do next? We somehow need to start parameterizing the solution that has this one spinner giving us our SU3 structure. We want to understand how do you actually write down such a solution, and what do you need to know about the space M6 to actually construct it. So a helpful tool in this is to build some nowhere vanishing forms out of eta naught. Yeah?
Just to understand the logic, so far you're deducing just the consequences of one?
Correct.
These all just...
So basically, I took care of this guy with maximally symmetric, and then one, and then the last one in the heterotic theory involves the gauge field, which I haven't talked about yet. Other questions? Yep. So all of this so far is just demanding n equals 1 supersymmetry in 4D, this one nowhere vanishing, not quite covariantly constant spinner. We've reduced the structure group of the frame bundle down to SU3, and now we're going to try and characterize that from a differential geometry point of view a bit more explicitly. Okay, so it's helpful to build some nowhere vanishing forms. Using this eta naught, we can build a two-form, Jij, which is the two-form over the compact manifold M6. Here, gamma 7 is product of gammas. We can build a two-form and a three-form, which I will write as omega, which can be expanded in terms of real and imaginary parts, with omega plus ijk minus I eta naught dagger gamma ijk eta naught, and omega minus conjugate is minus gamma 7 ijk eta naught. Okay. So from these forms, you can show using overall normalization and the Fuchs identities on spinners, you can show that these must satisfy the following conditions. So let's say Fuchs identities imply that J wedge omega is 0, and J wedge J wedge J is minus 3 over 4i omega bar wedge omega. Okay. So now we're starting to set ourselves up with a problem in differential geometry. We're saying I want a compact 6-dimensional manifold that admits this nowhere vanishing spinner, but now we have some structure about 2 forms and 3 forms that exist over it that must be nowhere vanishing. And we're demanding that this is SU3 structure. So how do we classify the possible solutions? What is going to go into that classification? Of course, we want to topologically describe the spaces, but at the end of the day, you would also like to know that a metric exists that's going to solve your equations of motion. And in the context that I'm illustrating with here, we also have things like this 3-form. Here I'm pointing at one component of it, but in general, the 3-form or flux background of the theory also has to be specified. So you explicitly need to know what are the metric, what is the fluxes in background. So how do we classify solutions? Question mark. It turns out that there are relationships between this J and omega that are extremely powerful, and I will write them out. Bear with me for a moment as I write these big expressions, and then I'll define what I mean by these terms. So there is a parameterization of the derivatives of J and omega in terms of some other forms on the space. Plus omega. Where, I'll say just a tiny bit more. We demand that omega 3 wedge J is omega 3, omega is 0. Omega 2, sorry, that's not omega, that's W. W2 wedge J is 0. This is required for uniqueness for a unique decomposition. So the decomposition that I'm doing here will be unique if these are satisfied. And now these Wi, these are the so-called torsion classes of the SU3 structure solution. And let me say just a little bit more about them. We can make a table, which I will do here. So let's write W1. So here, W1 parameterizes these objects. In terms of SU3, it's a 1 plus 1. And this is actually a function as part of the background. W2 characterizes d omega a 2 comma 2. Part of this where this denotes complex structure, 8 plus 8. This is a 3 form. W3 is dj, which is 2, 1 plus dj 0, 1, 2. This would be 6 plus 6 bar, again, a 3 form. W4 is j wedge dj, 3 plus 3 bar in terms of SU3. This is a 1 form. And W5, d omega 3, 1. This is 3 plus 3 bar, also a 1 form. Okay, that was a lot to write out. What the heck am I doing? In general, at this stage, all I know back here is that I can build nowhere vanishing forms out of the spinner. You might be like, why would I now try and rephrase all this in terms of these random W's and this sort of arbitrary differential geometry structure? The reason for that is if I hand you some mystery manifold, or worse yet, I don't hand you, I say go find some mystery manifold that has some covariantly constant spinors for which I can build these forms, this is extremely hard. And by extremely hard, I mean effectively no procedure exists in the mathematics literature to do that. So we don't know how to solve that, but it turns out that if you are interested in parameterizing these closed forms over a compact manifold, using the torsion classes, in principle, if you can find yourself some torsion classes in background that are of this form, that transform under SU3, and then you can sub them into an equation like this, you can explicitly build the J and omega. This is still hard, but it begins to be tractable from a differential geometry point of view. So these torsion classes are the modern way of trying to study SU3 structure solutions. If you look in the very old literature on flux compactifications of string theory, this was not always phrased in this way, but this, over the last 20-odd years, is how the field has sort of organized itself to search for solutions of this type. In terms of what I've written, I have not imposed the full structure of heterotic string theory. Everything I've written here is actually fully equivalent for n equals 1 solutions in 4D across many different string compactifications. So we could consider SU3 structure compactifications of 2B, 2A, et cetera, many other types of string theory. So far, so general. In the case of heterotic string theory, you can then go to the full equations of motion of the theory. The other supersymmetry variations that Rajesh mentioned a minute ago, I had not fully imposed yet. And you can go back and impose those and say, what do I need in terms of these torsion classes in order to have an actual solution to the heterotic theory? So in case of heterotic, which is the arena I'm illustrating here, it turns out that in order to solve equations of motion and full SUSY variation, you need that W1, W2 are 0, W4 is a half W5 and is exact, and W3 is free. A solution of this is called the Hull-Strominger system. In the case of heterotic string theory. Okay. In general, how would this be different if I were doing a different string compactification? So for example, if I were doing a type 2 theory, what would happen? You would have still the parameterization in terms of this basic geometry of J and omega, but the particular torsion classes you would need to turn on over that solution would differ depending on which corner of string theory you're looking at. So different torsion classes, but same structure for the basic SU3 structure manifold. Another comment just on terminology, you might be wondering, as I've written it here, why are these called torsion classes? And that is because of the condition that we were considering in building these, right, was something that looked like a derivative plus h acting on eta naught is 0. I said that wasn't quite covariantly constant. It is, however, the case that, recall, so just this is an aside, recall that in general relativity, differential geometry for a Riemannian manifold, if you have the commutator of two things acting on a vector, this of course gives you the Riemann curvature tensor, mu lambda v lambda, plus torsion. That's right. Right, like this, plus a torsion term that is proportional to the covariant derivative of your vector. My index structure is slightly funky here. Sorry, I'll put my vector back up. Okay. In general relativity, we take the Christoffel connection, for which we turn off torsion, right? So we choose the unique metric compatible torsion-free connection. If you don't do that, you can define a different connection on this SU3 structure manifold, such that this operator, which is d plus h, equals 0, this can be upgraded to a different covariant derivative with torsion acting on eta naught is 0. So there is a notion of which you have a covariantly constant spinor on the space, but it's not covariantly constant with respect to the Christoffel connection. It's a more general torsion-full connection. So there we go. There's some torsion classes. Okay. Yeah.
Is
Mm-hmm.
This is you're taking the 3, 1 piece of d omega.
Correct.
But then, how is it a 1 form? I mean,
Under like a star.
but then it's 2 form. I mean, you pick the 3, 1 piece. 6
Right. So this is. So let's talk just in terms of real structure for a minute. So this would be a 4 form, right? And then in terms of, yeah, the 4 form over the full space. And then the 1 form component of this, sorry, I actually realized there's a slightly, let me defer that question for a moment. You're right, there is a 1 form part, but I haven't talked about how to pull it out yet. Hold that thought for one.
for the d omega 2, 2 as well, right?
Yes, also you have to say a little bit more, but let me come back to that in just a moment, if that's okay. Okay. Good. So now the question is, we have some set of omegas in background. We want to find the allowed j's and omegas. As I mentioned before, directly solving for the spinors is really tough. The basic plan, and that's where, for example, the heterotic Hull-Strominger solution comes from, is to rearrange the equations of motion in terms of constraints on the w's. In the case of the Strominger solution, so let's do the heterotic case. So I haven't written this out, but this is from the equations of motion from the 10D Lagrangian. So just solving both the spinor variations and the equations of motion. Non-trivial calculation, which I'm not going to do for interest of time here. You can rearrange all of them into conditions on the torsion classes, and these are necessary for a solution. So this is what Hull and Strominger showed.
So that's a stronger condition than just the supersymmetry variation?
Correct. So that's not just having SU3 structure. Now that's SU3 structure in the presence of the heterotic equations of motion. There's also, this is just the condition on the manifold. There's also conditions on the gauge field that they must satisfy a Hermitian-Yang-Mills equation, which I have not written also. But in terms of the manifold, this has to be true. It's also worth mentioning, because I'm starting to allude to it here already in my slightly confusing answer to this, in terms of breaking this up in terms of complex structure. In the case of many of these solutions, and in particular the Hull-Strominger solution, you can show that for these structure of torsion classes, the solution is always complex. So there's a notion of, this is an even dimensional manifold, and there's a natural complex structure you can define on it. Okay, so let's return to the Hull-Strominger system. Importantly, in general, I should add here that in the search for these solutions, you really have to build it, right? You have to find some manifold. You have to explicitly show that, there exists some forms with this structure on it. You have to verify that it's SU3 structure, and you have 0 existence theorems that this works. So for many classes of topological manifold or, attempts at different W's that you're going to try and turn on in background, there are no solutions. And even with this structure guaranteeing that you have a Ricci flat metric on the space, as we'll talk more about in a minute, also very hard to achieve. So in general, there's no guarantee this is going to work, but this is the general setup that you want to try. Okay, so back to the Strominger system. We had W1, W2 is 0. W4 is W5 over 2. This turns out to be D of the dilaton, and W3 is free. It turns out, however, that this can be balanced with correct choice of flux. So this can effectively, with flux background, i.e. H not 0, this can be balanced or absorbed into your solution. Importantly, I haven't talked much about what the structure of the 4D effective theory arising from this will look like. We'll come more to that later. But in terms of n=1 theories, we can parameterize the potential of that in terms of D and F terms. And of course, the superpotential of the n=1 theory. So 4D n=1, you can show that the Gukov-Vafa-Witten superpotential this takes the form of W is this omega wedge H plus I dj in the case of SU3 structure. And this guy is loosely related to W1. This one is related to star of W3 after solving the equations of motion. And so importantly, the choice of these torsion classes will determine the 4D superpotential. So if you can find the torsion classes, you can specify a lot about the structure of the 4D theory already. I've said this briefly before, but let me say it more explicitly. In any of these solutions, if you have W1 and W2 equals 0, the solution will be a complex manifold. And if dj is 0, this gets upgraded to something stronger, which is a so-called Kähler manifold, which we'll define further in a moment. The fact that omega is an element of H naught of wedge 3 of the dual cotangent bundle. If you haven't seen this before, H here refers to forms that are closed but not exact. So the cohomology group of the associated tangent bundle, or in this case, dual tangent bundle. It's third antisymmetric power. This is just structuring the form structure of this omega. This nowhere vanishing has a consequence, which is that topologically it tells you that this has to be the trivial bundle. And hence the first Chern class, here I'm referring to my space X, as this is X6 now. Previously I was calling it M, but now in the case that this is true, we'll call it X. C1 of Tx is 0, where here this is the first Chern class, which is roughly trace of the field strength for any bundle. This is nice because it tells you that there is a broad topological classification for these SU3 structure manifolds. Their topology must be such that the first Chern class vanishes. And in many cases that we'll be interested in, we can use the power of complex geometry. This is really not to be underestimated because in differential geometry, anything that you can do in complex geometry is generally much easier than anything that you have to do in real differential geometry. So it is worth the simplification. Let me just, actually, no, let me not do this aside yet. Good. So for heterotic string theory, we've constrained the SU3 structure manifolds in play, and we can ask about what solutions are known. So I've argued there's this general structure. We can parameterize everything in terms of torsion classes. So far, so great. But now, can you actually do it, is the question. And the answer is only barely. So there is a very broad, simple class of solutions, and then the more general class, we have to really work hard to find new solutions. So, write the following. So what solutions are known? Here's an example. Let's consider W1, W2, W3, W4, and W5 all equal to 0. If that is the case, then your 3 form as part of your background geometry is 0. The dilaton is constant. There is no flux or torsion in background, and instead, we have a legit covariantly constant nowhere vanishing spinner. In this case, SU3 structure upgrades to so-called SU3 holonomy. In this case, the SUSY condition, Rij is 0, and so this manifold is Ricci flat. at least to leading order in alpha prime. Okay, this is, of course, a famous class of solutions. I'll define this more in a moment, but this is the so-called Calabi-Yau solutions. As a brief aside, we'll start with a non-trivial solution in a moment. Let me just comment on holonomy versus SU3 structure for a moment, and a very nice classification that is well known. So if we are interested in SU3 holonomy rather than SU3 structure, there is something called Berger's classification. For all possible holonomy groups in any number of dimensions that manifolds can have. So here I've been interested in the case of a 6-dimensional compact space, and I've been interested in n equals 1 supersymmetry in 4 dimensions. But more generally, for any set of dimensions here, so let's say dim n, I'm interested in holonomy, and the type of solution. When n is 2m, then Berger showed that if I am, by the way, neglecting product group structure in holonomy, so not reducible manifolds, but irreducible. This is special. So this is exactly the case that we just found for SU3. So 6 over 2 is 3. In this case, these are Kähler, Calabi-Yau, and Ricci flat. When n is 4m, you can have SP n over 4. These are special holonomy, hyperkähler. Also fall in this category. And here's the real reason I want to highlight this to you. N equals 7, G2, and n equals 8, spin 7. So these two cases are exceptional, and also not Kähler or Calabi-Yau, but are Ricci flat. So in terms of possible holonomy groups for compact manifolds, we can see that this SU3 holonomy lives in a very special list of limited possibilities. Notice these higher ones that aren't the Calabi-Yau case. These are all going to be very simple and sort of restricted solutions. For example, this will only be interesting in 8 dimensions for the compact directions. N equals 7, G2, this will be interesting for compactifications of M theory, which I'll return to more, or N equals 8, spin 7. Just as an aside, I've been doing this in the context of heterotic string theory, but I just wanted to mention this more general classification of holonomies. In each case, these holonomies can be upgraded to the associated structures. So if we're in 7 dimensions and we are looking at G2 holonomy, if we turn on flux in background, we can upgrade that to a G2 structure. I've written everything in terms of torsion classes for the case of SU3 structure and SU3 holonomy, but you can do a very analogous computation in the case of G2. There, for example, you would again be demanding that you have a covariantly constant spinner in background, reducing 11-dimensional spinners, so the structure would work very similar. So the point here I just want to make is the structure we're setting up, holonomy and structure, looking at these spinners, all of this works for other corners of string compactification as well. Yeah? Good. So we could also consider non-Ricci flat. I'm going to not get into all of those right now, just because that'll be a bit longer to explain, but Bobby is very right that we do not have to consider strict Ricci flat solutions. So depending on the flux backgrounds that you're choosing, you may get deformed away from a Ricci flat solution, and you want to consider non-trivial curvature of the compact dimensions, and that will increase this set further and in interesting ways. So let's hold that thought for just a moment. We'll come back to that as well if we can do. Before we get deep in the weeds of different possibilities, let's look a little more closely at the case of SU3 holonomy.
Can I ask a question?
Sure.
So the first Chern class being 0 is I thought that meant that this becomes a Calabi-Yau, but
No. So
No.
if it's Calabi-Yau, its first string class is 0,
Uh-huh.
but it is broader than that. So if you say first string class is 0 and Kähler, then Calabi-Yau.
Okay, so
But not necessarily Kähler still has first string class equals 0.
Okay, so that condition does not mean that it's scalar. Okay.
Correct.
Thanks.
Yep. Okay, that being said, I am immediately going to go to the Calabi-Yau case to talk in a little bit more depth about what's understood. And this is the corner of the, string compactifications and the study of their effective theories. This is the corner that's been developed the deepest. Not because it's preferential from any phenomenological point of view, right? The general structure we've set up here. But as I'm going to try and illustrate over the next couple of lectures, it's really hard to find these solutions. So the Calabi-Yau context and SU3 holonomy, this is where we've been able to push these computations the furthest and study in the most detail. So this is really about computational viability, which is not the most principled reason to study something, but is still important in terms of being able to actually extract some physics. So very related to the question we just had, let's define what we mean by a Calabi-Yau manifold. Calabi-Yau manifold is a compact, complex manifold with a, in fact, unique Ricci flat, and here's the key word here, Kähler metric. Recall, Kähler is the condition that dj is 0 in terms of this 2 form that we just defined. In terms of complex coordinates, we'll write that as GAB bar, complex chords. And here's the real power of this class of solutions. Thanks to Yau's proof in 1977-78 of Calabi's conjecture, the following is true. If you have SU3 holonomy, C1 is 0, and Kähler, then you have Ricci flat. So if you know that you have a Kähler C1 equals 0, sorry, I wrote just generally C1 here, C1 equals 0 solution that is Kähler, then you know that there exists a metric that will solve your equations of motion, in this case for Ricci flatness. This is the real reason that this is a powerful arena to actually be able to compute things, because you have an existence theorem that tells you that a metric that you want exists. You can ask, do we know that for any other cases of SU3 structure, torsion classes? And the answer is almost none. So in almost every other arena, we don't know for sure that solutions exist. But here we do. You can ask roughly how many solutions exist, and there are more than 500 million constructed so far. An important question that I'm going to come back to in lectures later this week is the set of even Calabi-Yau threefolds, which is the easiest possible type of SU3 structure solution to consider, is it even finite? That has not been proven mathematically, but there are actually very strong approaches from the physics literature that indicate that perhaps it is, and I'll sort of summarize some of the modern understanding of how that goes. There are also known solutions. So here in the case of Calabi-Yau, again, I've focused on the manifold, but we have other solutions, other parts of the background solution to specify. So in the case of heterotic string theory, we also have to ask what's the 3 form and what are the gauge fields doing in background. The 3 form is set to 0 in the case of a Calabi-Yau compactification, but you still have to ask what solutions to the gauge field do you have? Unfortunately, for the Strominger solution, solutions to full Strominger solution with CY3 are abundant. So there are many known solutions for gauge fields that will solve the full system. For example, one famous one is to set the spin connection equal to the gauge connection. That is to choose your background gauge bundle to be the holomorphic tangent bundle of your Calabi-Yau. And in this case, all known CY3s will work. So you can always, as an example, choose a gauge field to be the tangent bundle to your manifold, and then you have a full solution to the theory. Just looking at the clock here, I think this is roughly my official, am I at time? Do I have 15 more minutes? Oh, I have 15, okay, I got it wrong. Sweet, I gotta keep going. Okay, so that is one, at least, class of solutions that's available. There are, of course, many others. All right, let's do a non-Calabi-Yau solution just to give a feel for what else is known and how people approach the problem. And then we'll return to the simple case in a bit more detail to try and actually extract some physics from this whole process. So one class of solutions, Calabi-Yau. What if we wanted a class of heterotic solutions that were not Calabi-Yau? Here we need some way of constructing the SU3 structure. The trick that people use in this context is to try and bootstrap something that does involve this sort of simple Kähler geometry, which is much easier to define with algebraic geometry, and bootstrap towards something in real differential geometry. And the trick is to use substructure of the manifold that is easy. So example number 2 is the so-called Fu-Yau construction. And here the idea is to write down a manifold that involves simple pieces that are put together in a non-simple way. So if we consider, for example, a CY2 manifold, and over it we fiber a product of two circles. So what do I mean by fiber? I mean over every point in the manifold, you have hair on the manifold, i.e. you have a projection map from the set of two circles everywhere down to a CY2, which is of course a K3 surface. Just a quick aside on fibration structure because we'll need this. Again, fibration structure means that you have, if X is fibered over some base, this means that you have a preimage for each point in the base, which is effectively homotopic. So it means if you look over each point in the base manifold, if you pull back to the total manifold and then compare two different points or two different fibers, that they look like the same topological manifold at almost all points. That's the nature of a fibration. Okay. So Fu-Yau solution, also, as an aside, the explicit examples of this type were written down by Goldstein and Prikushkin. And Fu-Yau put in suitable gauge bundles that will satisfy the full equations of motion. So if you consider a product of two circles over K3, each of these are very simple spaces. Here, the full non-Kählerity, the full torsionness of this background is encompassed in the twisting of this fibration. So you have very simple ingredients that you twist together in a non-simple way to try and build explicit solutions. Here, people were able to, so I'll just say you can find, and this is what Fu-Yau did, find gauge fields for full solution to solve equations of motion and the Bianchi identity. And after much pain and labor, they can find roughly a 2-parameter family of twists to this vibration, which will work, but, and here's the big but, so this is a nice construction of more general SU3 structure solutions, but in general, all such solutions have small cycles. Why is this a problem? Because in setting up a 10D supergravity solution, I want to write down the 10D Lagrangian, and effectively integrate out those 6 compact extra dimensions to produce some 4D theory. I want to remain in the supergravity regime, which is large volume, and I want to have some control over the effective theory. If I write down a solution for which there are small cycles or volumes inside the manifold are extremely small, this will in general mean that non-perturbative effects are very large, and that the way that I am controlling the effective theory will break down. So I've used the supergravity limit to actually write down the equations of motion to say what solution I wanted. But if the solution itself has small cycles, there's no guarantee that I solved the right conditions to find that manifold, if that makes sense. So all of the assumptions that went into my derivation have morally broken down. And this is a generic problem in SU3 structure solutions, which is even if you think you're building something topologically of the right form, it may not be appropriate for the right regime of field theory that you need to extract physics. So, generic problem.
T3 has a complex structure, and the T2 also? Or is
The T2 is not, so this is, yeah, topologically S1 cos S1, but you're not writing it as a complex manifold. Independently, of course, you could do either one. So really, the badness is being introduced in the twist. So that's what's pulling you into the more general torsion solution, more general flux solution. And that's the beauty of this construction, is that the pieces are very simple. The pieces are Kähler, and you can write them down explicitly and algebraically, and you're up and running. But the full geometry now is in SU3 structure.
And the small cycles are in the K3?
Correct. Yeah. Also, the overall volume is frequently a problem. So not always for Yau, but in general for SU3 structure. You can actually see this from the structure of the Bianchi identity. So roughly you get, so DH is going like trace F wedge F minus trace R wedge R. And there's an alpha prime out here. If you have an explicit DH, you are frequently fixing the scale of alpha prime, and it does not have to be at the scale you wanted. So the overall volume can be fixed to be inappropriate, too small for the large volume approximation.
Because in the T3, I thought you understand the singularities in the K3 moduli space.
Oh, very much, yeah.
So
But the problem is for the full SU3 structure. Yeah, it's exactly this alpha prime that's the problem, right? So this is really about the value of the 3 form in background can be just such that your whole alpha prime expansion didn't make sense. Okay. So let me just comment, where did I get to? Comment briefly on this. So here I'm mentioning one class of SU3 structure solutions. There are a couple more, but there is very, very little that's been done systematically, and I would argue nothing that in general solves the small cycle problem is fully under control in SU3 structure, except for some very special cases. Why is this so hard? As I just alluded to, in general, in the heterotic context, the presence of this background flux is messing with your alpha prime expansion. So in general, it's pushing you out of the supergravity regime, and then again, you have to adjust which equations of motion you were going to solve if you're no longer in the supergravity regime. But in general, just mathematically, why is it so hard to find solutions for all these torsion classes of the form that we wanted? The main mathematical reason this is difficult is the difference between, in general, differential geometry, which is, of course, the study of metrics and connections and so on, and, quote, algebraic geometry. And this exists in the complex and Kähler regime. And as I'll illustrate more in the next lectures, in algebraic geometry, you can take very simple spaces, write polynomial equations in them, and find solutions. So this is basically a complex manifold upgrade of the very simple way that we have built shapes in RN our whole mathematics career, right? When you are a baby student and you want to describe a sphere in Rn, you write a polynomial equation to describe the shape of that manifold. That kind of trick, write some equation in some simple space, works really well in algebraic geometry, in the complex and Kähler regime. In differential geometry, in general, you have no tool to embed or explicitly describe the manifold. And that becomes extremely hard. So you just, abstractly, you need some starting point, some foothold to be able to build these things. So this difference with algebraic geometry I'm going to illustrate, and I'm going to show you how this gets, how these get built systematically in the case of Calabi-Yau manifolds. Importantly, I will comment that if you want to use the tools of algebraic geometry, so you want to be able to write systems of equations in spaces and then describe the resulting space, so note here, the only projective varieties of SU3 structure are Calabi-Yau. So what's a projective variety? This is a simple manifold that can be written as a system of equations solved in some Kähler space, basically. So if you have a simple enough ambient space, and this is where the main tools of algebraic geometry apply, then you're reduced to the Calabi-Yau context. Why is that? Just commenting, SU3 structure, of course, implies that C1 is 0, and here, having a so-called algebraic variety, this is our simple ambient space and system of equations. This leads to complex Kähler manifolds, and of course, due to Yau's theorem, we know that these two are equivalent to Calabi-Yau. So that is the trick. We're going to begin then, and I only have a few more minutes today, we're going to begin with the next lecture in earnest, writing down Calabi-Yau manifolds and understanding some of their properties. There are many very nice lecture notes on the internet about Calabi-Yau manifolds and their backgrounds. I'm going to do a fairly cursory overview of those sort of basic background features and focus more on some sort of modern questions about classifications, finiteness, and other structure of interest. But again, just to motivate, why are we considering Calabi-Yau? Because we need some way to actually compute solutions of the type that we began with, right? We began with a Lagrangian in 10D. We had equations of motion. You want to solve it. We need some arena where we can actually write down those solutions and then begin to extract physics. So the Calabi-Yau arena is a very robust one to begin to ask some of those questions. But to emphasize it again, it is extremely limited from the point of view of this general structure of solutions. So let's say it this way. Why look at Calabi-Yau's as a starting point? Basically, we are just beginning after 40-odd years with a sort of century of progress in algebraic geometry and 40 years of string theory, handful of Fields medals, to have the mathematical tools to extract necessary physics. But it is important to remember that what you can do and what you want are not necessarily the same thing. To finish, I will just comment, when I was in undergrad, I took assorted classes in differential equations. I had the first class in linear differential equations, and then you do nonlinear, et cetera. I remember one of my professors emphasized the difference between linear and nonlinear differential equations is like classifying the universe into bananas and non-bananas. It is true, but not very deep, right? Humans love linear differential equations because those are the ones we can solve, not because that's how differential equations are made. So this is going to be the banana category of solutions to start with. This is where we can make concrete calculations, but we should remember that non-bananas exist as well. So I will stop here, and we'll pick up with Calabi-Yau's tomorrow, and then push forward extracting physics. Thank you.